So there exist three charges of equal magnitude Q with the assigned signs as shown in the diagram. They are all arranged at the corners of a triangle. I've identified point P at the center of the triangle. R and S are located at the midpoints of the sides as shown. A fourth charge, also Q, and is positive, is to be placed somewhere in this arrangement. Assume that the triangle has side lengths S. I want to say find the net force, but after our discussion from yesterday, I'm going to find the electric field. It's not changing the problem much. It just means all of my answers won't have one Q in them. Is that okay? That way it's consistent with what we talked about yesterday. I'm going to draw a few lines as they are drawn here. It looks like there's an altitude that's been drawn from the very top to the midpoint of the side. Would you guys agree that this appears to be a equilateral triangle? So there's a certain amount of symmetry already inherent in that. And let's see, I'll have another one here. Looks pretty close. And a final one here. And these all meet at point P here. And we have point R here and point S identified there. Then I have one positive point charge located here, a value Q, and I have two negative point charges and they're located here. Now the first question says, please find the size and the direction of the net force, and we're going to find electric field. So for the electric field at point P. All right, so the electric field points in the direction of a force on a positive charged particle. So the first component to the electric field, I would say, coming from this particle, is going to be in this direction at point P. Any question about that? All right. The next component of the force, which by symmetry is going to be the same size force, but it's going to be in this direction for the negative charge to the left, and in this direction for the negative charge to the right. And I know that these have to be the same size forces because they are all the same distance away from point P. Any question about that statement? Okay. So I am going to have to figure out this distance if I'm going to want to be able to work this problem. And I'm also, I think, very clearly going to have to work out what that angle is. Go ahead.
Why is it in the chart, like, I guess I interpreted the question wrong probably, but I was thinking like the R, the P, and the S were just placing them differently, like they're not all three always there. So how would P get, like, how would P be influenced by R if R technically isn't there?
It's not being influenced by R. The red arrow represents the electric field component from this charge.
Oh, okay.
Does that make sense? Yeah. Okay. And the blue arrows are from each of these two charges. Is that okay? All right. So just keep myself working this in my head. Electric field is going to be equal to QK over the separation distance squared. It's just a magnitude part. I'll work the vector part out in a minute. Any question about where that came from yesterday? All right, so I'm good to go on. I need a value that I'm going to use for R, and I think I'm going to get it by looking at a right triangle that seems to present itself here in the picture. The right triangle I'm thinking about is, let me see. Well, maybe not that. Well, that's not going to do it, is it? How about, let's see. Welp. There's no accounting for the way the software works. I'm trapped using it. So let's see. There we go. So I see that right triangle. Does that work for you guys? Okay. With that right triangle, and I'm just going to do a little bit of figuring here. This length is, they want me to use S, right, for the side length?
Yes.
So this is S over 2 is that particular length. And I want this as R. So I know that this angle has to be 30 degrees. Right, because if it's an equilateral triangle, the entire angle is 60, and this bisects the angle, so that's why it's 30. I don't feel like I should have to explain stuff like that in this room. So if you couldn't put those things together and you're in this room, understand I'm doing that out of courtesy, but I shouldn't have to, okay? I see a 30, 60, 90 triangle here, but I'm going to go the long way here. Cosine 30 equals S halves over R. So R equals S halves over cosine 30. And my recollection of trig is that cosine 30 is root 3 over 2. So S over 2, root 3 over 2, or S over root 3. We all good? I would leave the root 3 in here. I wouldn't go to a decimal. Right, we got some squares coming up and everything. Just leave it. We probably got some more cosines or sines coming up too. So I would just leave it in place. But I'm going to be using this for the remainder of the question. So I don't need that triangle anymore. Nor do I need any of the things associated with it, really. Let's get all that out of the way. All right, so now I think I can assemble most of what I need, except I see a certain amount of exploitable symmetry. Do you guys see it? So I only want the component of one of these forces, since I have an equivalent component in this direction, right on both sides, and those two will cancel out, but I will have two components that point towards R, so I just want one of them. That all okay? Well, this has got to be 60 degrees. So if I just put E right now for that blue arrow, I think I want, for this component that's pointed towards R, E cosine 60 degrees. And that'll give you the component of E that is towards R. Any question about that? All right. So with my geometry done, I'm going to have, for the total electric field, one full value of E plus two values of E scaled by 60 degrees, the cosine of 60 degrees. Do you guys see what I've done there and why I'm doing that? This is going to be our total electric field. And the direction we'll talk about in a minute, but I think you guys realize the direction is going to be downwards. Now, E is going to be QK over R squared, which we now know is S over root 3 or S squared over 3. Any question about where I got that from? So I can write this as 3QK over S squared. That's what I'm going to use for E. Factor out the E, and I'll get 3QK over S squared. And in the parentheses, I'm going to have 1 plus 2 times cosine 60, which is a half. And it looks like my answer is going to be 6QK over S squared, the total electric field due to the 3-point charges. If you're trying to find the force, well, force is just going to be Q times E total. So you'd have Q squared there. So please find the size and the direction of the electric field when it's placed at point R. And is this electric field greater or less than when it was at the center? Alrighty, so we're looking at R now. Well, if I use the same argument from before, meaning I see 3 charges there, each one applying an electric field, I think there'll be an electric field from the top charge at point R in this direction. It's probably going to be less, though, than what it was a moment ago. I'm also going to have an electric field component in this direction from the charge on the left, an electric field component in this direction from the charge on the right, but I think those are going to cancel out. So I believe the only component that I need that matters is the one from the positive charge. But I'm going to need this distance in order to complete that. Oh, making sure is important. This is our triangle, and I make mistakes. I get in a hurry. This is 30 degrees. So I'm thinking cosine 30 equals R over S. So yeah, looks like it. I was just hoping to use what I did last time, but I should have been smarter and done the work a little bit clearer. So root 3 over 2 equals R over S. So R is root 3 S over 2. Yay. At least one of you had the courage. So did you give Google that win? Goku that win? Do you win? Are you the winner today? All right, that's fine. So electric field's going to equal QK over, 4 3S squared. I think math is still working for me though, even if geometry's not. Any question there? All right. So now we're stuck with the last one. The last one's not going to have the symmetry we had before. And we have choices on how we can approach doing this. But I think since I'm doing this in front of the class and I don't want to do anything there's no reason to do anything weird, I'm going to approach the last question kind of just brute force our way through. Okay? So if this is our point S, and we're trying to figure out what the total electric field is at S. And I say this one is really challenging. It's challenging because there's no symmetry here. We're going to have to find components of the electric field in the X direction and components of the electric field in the Y direction. Or we have to change the coordinate system that we're using, but I'm pretty sure we're going to use the same coordinate system that we've been using, with Y being vertical and X being horizontal. All right? Now you don't have to do it that way, but since the problem was presented this way, even if you rotate your coordinate system, you'd have to rotate it back for your final answer. So let's just go ahead and see what we're up against here. I think there will be an electric field in this direction due to the red charge, the positive charge. I think there will be an equal electric field in this direction due to the blue charge in the bottom left-hand corner. And I believe there'll be another component of the electric field, albeit smaller, along this line. Any questions about those choices? Okay. We've already measured all these distances, so we don't have a whole lot that we have to do when it comes to the distances. But when I look at this, I recognize that X is going to be considered this direction. and y is going to be considered this direction. So if I want to find the net electric field, this problem has really two more parts than we had before, because we didn't have symmetry before. So, I'm sorry, we had symmetry before and we don't have it now. So we need to find all of the components of the electric field in the y direction, and then all of the components of the electric field in the x direction. And when that's all done, we need to find the direction of our resultant electric field and the magnitude of our resultant electric field. Everybody okay with what I just said? There's a lot there. So we're going to take this in small steps. But luckily for us, there's a little bit of repeat work we get to do here. So I'm first noticing that this has got to be 30 degrees, and this has got to be 60 degrees. That all okay? So I'll have two components in this direction and a component in this direction. And I will have three components in that direction. Did we see where they're all going to come from? So I'm going to save myself a little bit of heartache. I'm just going to call this E1 over here for these two and E2 over here for these two, just for the portion of this where I'm breaking up components. And then I'll plug in the size and magnitude of E2 in a minute. That okay with you guys? All right. So based on what I have here, let's do all the electric field components that are going to be in the x direction. There's going to be, and I'm going to make this negative, this positive, and this, I guess, negative to be consistent. I'm going to have 2 times E1 sine 30 in the negative direction, plus, let's see, E2 sine 60 in the positive direction. Those represent the electric field parts that are going to be all along the x direction. Is there any question about where any of that came from? Okay. And then in the y direction, looks like I'm going to have negative 2 times E1 cosine 30 minus E2 cosine 60. Okay. I feel pretty okay about all of that. Do you guys feel okay about all that? All right. So now I need to come up with an expression for E1 and E2. E1 looks like it's going to be based on this distance. We already know what that distance is. Well, maybe. I tried last time. Then I was failing, but I'm pretty sure we can still do this. What's this distance going to be from before? Huh? Just half of S, right? Okay. So if we're going to use half of S, then E1 is just going to be QK over half of S squared, or S squared with 4 over that. Is that okay? Any problem? All right. E2, we're going to get that Q and K again, but this time the S is the distance we used before, this one, which I got wrong, so I need to be careful here. I don't want to mess it up again. Square root of 3 over 2 times S. So it'll be square root of 3 over 2, so 4, 3S squared. I'm okay with all that. Are you guys okay with all that? All righty. So, I find this to be a little distracting now. We don't need the picture anymore, right? So I can just slide this off to the side a little bit, and I'll start with my x portions. So I'm going to have -2 times 4qk over s squared sine of 30 1/2 plus E2, so 4qk over 3s squared, sine of 60, so square root of 3 over 2. So this represents the x direction. And we can simplify this a little bit. Not that much, but we can simplify it a little bit. But let's just hold off for right now, and let's do the same thing for the y direction. So y direction, I've got -2 E1, so 4qk over s squared, times the cosine of 30, so square root of 3 over 2, plus, minus E2, which is 4qk over 3s squared, times the cosine of 60, so 1/2. This is all in the y direction. It's icky, I know, but bear with me for a minute. Everybody okay? I am noticing that in the x direction, every term has a 4qk over s squared in it. Are you noticing that too? So I'm going to take 4qk over s squared out, and what's left is -2 times 1/2, so -1, plus root 3 over 6, I think my algebra is good. My arithmetic's okay. Are you seeing the same arithmetic? So I can move on. I have the same thing I can pull out in the bottom one too. 4qk over s squared times, looks like that -2 and that 2 will cancel. Now let's have -√3 and minus 1/6. How's that? That all okay with you guys? All right. So √3 over 6 is definitely less than 1. So I see that I have a component of my electric field this way. And I'm just we know that the whole thing has this term in it. So I only care about this part for right now. Is that okay? Because they're all going to be multiplied by the same amount, this 4qk over s squared. So what I'm just trying to do is build a triangle and get the proportionality of the sides right. So right now, this is -1 plus √3 over 6. So that's in the negative x direction. And this one is going to be -√3 minus 1/6. So we need the hypotenuse and the angle. I think tangent's going to give us the angle, and I think Pythagoras is going to give us the hypotenuse. I think I'm good, right? So let's. I mean, I don't really want to do the arithmetic. I mean, can you do the arithmetic, or do you need me to do the arithmetic? I mean, you can get decimals now if you want. You don't have to keep them like this if you don't want to. I just did it like this to get to this point. So the top is just a number, whatever 1 minus √3 over 6 is. And the side is just a number, whatever root 3 minus a sixth is. And then you're going to square it, take the square root, right? So can I stop here, or do I need to continue? I leave it to you guys. I've got some thumbs up around the room, so we're all okay. Heavy lifting's been done. All right. Now, if this were me and I was doing the problem, you'd probably have to give reference as to what your angle is. You could give it from the positive x direction and do the whole that thing. You guys are familiar with ways you can express the direction of your answer. This problem would probably be more likely to ask you what the magnitude of the electric field is, as opposed to caring too much about the angle. But if you don't have symmetry, you have to do it this way. So if you have an asymmetrical answer, you'll need to break up your answer into components. Find the size of the components, and then from there, combine them to get your answer. There's really no other way around it. This is just a pain, and I'll be honest with you. It's more work than you'd probably be asked to do on an exam. Give me 1 second to work something out. All right, so will that do, or there, is that better? Not really. Come on, you can't match your own black, it's your thing. You guys make me crazy. All right, here we go. So I think we want the point right about there. That's the center, pretty close to the center. And they tell me that this is R, and that the whole thing has charge density lambda. So derive an expression that could be used for dq that could lead to a solution for the electric field at point O. So I'm going to choose a piece of length, say right here, and I'm going to say that that's my dq. I need to find out how much charge that has. Well, you're not going to like what I'm about to do because it's so kind of straightforward, but I'm probably going to say that dq just equals lambda ds, because lambda is charge density. It's in terms of coulombs per meter. So I just multiply by how big my piece is, and my piece is ds long. But that's probably not as, I probably don't want to integrate over that. So I will probably replace ds with, say, r d theta. That gives me a more integratable expression, because that way I can integrate across the angle that describes the arc. That's probably what I would use. Now, if they asked maybe another question, I don't think it's even there, but what is the charge on this arc of charge? Can you kind of give me an expression for it? Can't use Q. It has to be in terms of lambda. Excuse me? I couldn't hear you. All right, so yeah, I'd say charge is going to have to be equal to lambda times r pi. That's how much charge there is. The charge density is lambda, that's charge per meter, and r pi represents the length of a semicircle. So yeah, that's how much charge there is total. Sometimes we lose that idea that, well, I don't know how much charge there is. That's how much charge there is. In fact, I would expect in my answer, I'll probably see something about the total charge in there. Kind of have an idea, it'll show up. But who knows? Is that all you need to see? I'm just doing homework. Tomorrow guys are gonna do something for me. You don't really get what I did? Okay. So if you think back to our conversation at the beginning about this, what we wanted to do was create a ratio. And our ratio was charge to length is going to equal piece of charge to piece of length. Does that make sense? Well, they gave us something we have to use for this. They told us that that is lambda. That's the charge density. So they gave us what we have to use in place of Q over L. Does that make sense? Well, that still has to equal dq over ds. Our piece of charge times our piece of length. The only thing I did after that was consider rewriting ds in terms of r d theta. Because if we're going to try and define where that piece is, and I assume that this location I've just marked is, say, 0, then if I sweep out to where this point begins, an angle theta from 0, the size of this piece could be described by how big this piece of arc length is. And that's going to be based on how much theta we sweep out. We sweep out a little bit in the direction of theta. So using that thing from last year where S equals r times theta, we're just saying ds is equal to r times d theta. Small piece of length is equal to r times a small piece of angle. So then we just solve that for dq. Is that all right?